Hello, and thank you for attending today's webinar, New Cylinder Optimization Process, brought to you by System Seals, the Fluid Power Technology Conference and Fluid Power World magazine. We would like to thank our presenter, Kurt Sassmanhausen, for being here today. I'm Mary Gannon, Managing Editor for Fluid Power World, and I'll be your moderator today. Before we get going, here are a few words about our upcoming event, which takes place next week in Milwaukee. We are happy to invite you to the Fluid Power Technology Conference that will take place next week at the Milwaukee School of Engineering, May 16th and 17th. The conference will bring together fluid power professionals to learn from experts during technical sessions and network with industry peers. We have keynote speakers, including Alan Carlson and John Thornton, who will take a look at the future of fluid power. For attending this webinar, we are offering you a 20% off your registration when you use promo code WEBINAR20 at checkout. For the full lineup of speakers and the detailed schedule, please visit fluidpowertechconference.com. And now, just a few quick housekeeping details before we get started. You will see several boxes on your desktop, all of which can be moved around to suit your preferences. Initially, the Q&A box is at the lower left, and this is where you will enter all your questions for the Q&A session after the presentation is over. Another box to note is the additional resources, initially at the lower right-hand corner of your desktop. These resources are for your information needs. We also have a tweet box right on the desktop, so feel free to tweet any interesting points right from there. There's a list of hashtags for you to use as well. And importantly, we will be playing a few videos today. In order to stream properly, make sure to close any additional windows or applications you may have open. If at any point you can't see or hear the webinar, refresh your browser. If this doesn't work, click the Help widget. Now, please allow me to introduce your presenter today, Kurt Sassmanhausen. For the past 5 years, Kurt has overseen product and material testing with System Seals in Cleveland. He conducts research on material characterization of elastomers, thermoplastics, and thermosets, and tests for hydraulic sealing applications and statistically designed experimental methods. Major research projects have included cylinder side load, fluid compatibility, friction analysis, and seal failure modes. Kurt earned his bachelor's in mathematics from Cleveland State University and has a master's in mathematics from the University of Washington. So without further ado, I'm going to hand the microphone over to Kurt. Thanks for being here today.
Good afternoon. As Mary mentioned, my name is Kurt Sassmanhausen, and I am the Research and Development Manager at System Seals in Cleveland, and we'd like to thank everyone this afternoon for attending this webinar regarding our cylinder optimization process. And Mary did a nice job handling all of the technology and housekeeping stuff, so I think we're going to get right into the material. So what is the COP, or the cylinder optimization process? So over the last 5 years, and even extending back further, this COP process has really evolved out of a series of research projects that System Seals has undertaken and test programs that we've implemented over the last 5 to 10 years. And out of these test programs, we've been able to extract relationships, material properties, and a lot of mathematical formulations and relationships between various cylinder sealing components. However, the cylinder optimization process is more than just advanced algorithms and engineering tools. It's a sequential process that evaluates the interactions between all of the sealing components that go inside a cylinder in order to optimize the performance and reduce the long-term risk in hydraulic applications. So as we go through this presentation, we're going to take a look at not only each step of the process, but how each step relates to the others. So let's take a look at what the basic flow is for the cylinder optimization process. So the first step in the cylinder optimization process is that we need some information from our customers. Usually a dimensionalized AutoCAD drawing. This would include all of the dimensions related to the cylinder, the piston, the rod, and any existing sealing components or guidance components. And then something that we call the stamps. So this would be the speed, temperature, application, media or fluid, the pressure, and the size of the application. And from this, we're able to put these variables into our first calculation, which is a side load calculator. And this calculator allows us to determine what is the side load in the system and how can we appropriately distribute that load across the bearing components within the cylinder in order to minimize risks. After we perform the side load analysis, we move on to something that's called an extrusion analysis. So we're trying to understand which seals or materials should be used for the respective sealing components in order to ensure that they don't extrude under the system gaps and under the system pressures. After those seals have been selected, we can move on to a friction analysis. And after the materials have been selected based on the friction analysis and the extrusion analysis, we can also complete a chemical compatibility investigation. And we'll talk a little bit more about how this particular chemical compatibility investigation is a little bit more broader. It's a little bit more thorough than what you typically would encounter in standard material investigations. Finally, once we have the seal package selected and all of the additional supporting components, wipers, and guidance components, we can make surface finish recommendations for the system. And as an end result, our customer receives a proposal drawing, a COP report. So this would be a report detailing the analysis for each one of these 5 steps, as well as the chemical compatibility report as a separate entity. So why do we need to do a side load analysis in the first place? So if we look at this diagram or this drawing in the left-hand corner of the slide, we see that the traditional method for sizing guide bands involves simply assuming a load, a force that's being applied to the guide band, and although the guide band is circular, the assumption is made that that load distributes evenly and linearly across a rectangular projection of that guide band. And so it effectively takes a 3D circle, projects it down to a 2D, a two-dimensional surface, and then distributes that load over that area. And as long as the area is large enough to carry the load without exceeding some minimum specified stress value, traditionally the guidance system would have been determined to be acceptable. There's a couple problems with this particular method. First of all, it assumes the side load. So in many cases, the designer is asking the customer, what is the side load for your cylinder application? And the end user's response is oftentimes, I don't know, maybe it's 2% of the drive load, is it 5% of the drive load, I'm not really sure. And so now the engineering team has to make some assumptions. Secondly, this method ignores the angle of contact between the rod and the guide band. So if we think about a circular cylinder with a rod coming out of it, we know that everything doesn't really live exactly on center because of machining tolerances. There's a little bit of play in the system. And depending on the stroke position of the cylinder, that play is going to result in angularity. And that angularity results in a non-flattened area of contact between the rod and the guide band. So the guide band effectively has a load leaning on its edge because the rod is coming out of the cylinder with a slight angle associated with it. And the third issue with this method is that it ignores the nonlinear behavior of the stress distribution on the guide band. And so in the next slide, we'll take a look at what this actually looks like. So the upper left image on this slide shows us a semi-section of a guide band. You can imagine a rod resting on that guide band. But if you notice, the area of maximum stress is around the 6 o'clock position in the front of the guide band. That's because that's the area that sees the most stress. And because the angle of contact between the rod and the guide band is on an angle, not flat, moving from the front of the guide band to the rear of the guide band, the stress decreases according to the curvature of the rod. Moving from the 6 o'clock position to the 3 o'clock position, or symmetrically to the 9 o'clock position, the stress also decreases nonlinearly because we're dealing with a circle. So if we look at the image on the right, we can actually see what that nonlinear stress distribution looks like over the guide band. So instead of the guide band carrying that load in a nice, even, flat manner where you could say, well, maybe there's 20 or 40 megapascals or 2,000 psi of contact stress, there's actually a stress profile where the leading edge of the guide band at the 6 o'clock bears the brunt, and the stress decreases in a curvilinear manner depending on which direction you go, investigating through the guide band. This is why the traditional method doesn't work very well, because it doesn't capture this behavior. So one way to get to how this stress distribution looks is to run an FEA analysis. And so let's take a look at a video that shows us what this FEA analysis reveals regarding the nonlinear stress distribution on guidance components. So we're looking at a sectioned view of a hydraulic cylinder with spherical bearing ends, and for an exaggerated purpose, we are increasing the frictional torque that would occur at those bearings when the cylinder drives. And what you observe is this nonlinear stress distribution being superimposed on the guidance components. It occurs on the rod guide band, so this would be the larger guide band in the front. And again, you can see at the 6 o'clock position in the front is where the majority of the stress occurs. And it also occurs on the piston guidance component, but to a lesser degree, because the piston generally keeps the system flatter in that region of the cylinder. And so here we see the nonlinear stress distribution each time the cylinder would stroke or experience a bending load. The problem with FEA is that it's expensive and it's time consuming, and depending on what assumptions are made with an FEA analysis, for the same exact cylinder, sometimes you can get differing results depending on who is doing the FEA analysis or what parameters are selected. And so to get around the problems with time and expense and user variability, we've developed a COP side load calculator. And what this calculator does is, first and foremost, it actually calculates the side load that the cylinder is experiencing based on the operating parameters and geometry of the cylinder. So instead of us asking for information about what the side load is, based on the application and the cylinder geometry, we can tell you what that side load is going to be. And once we have that side load figured out, we're able to calculate the nonlinear stress distribution on the individual guidance components. We're able to optimize the number, the size, and the specific material for each guide band, determine the friction from each of the guidance components, and also determine the bending that the cylinder rod undergoes when it's experiencing this side load or this load out at the interface at the end of the rod. So let's take a quick look at a demonstration of this calculator, see how it works. So the first thing you'll notice is that the engineer is going to enter inputs into this calculator that relate to the dimensions and operating parameters of the cylinder: fluid type, density, material conditions, geometric representations and dimensions of the cylinder. And once all that information is entered, the engineer can now choose a starting guide band package. So we don't know what the optimum package is yet. We have to start somewhere. So we choose a traditional guidance package, traditional sizes, traditional spacing. And once those components have been selected, the engineer will now run the COP analysis. So they engage an iterative solver which winds up a solution. It hunts and converges for the solution for the nonlinear stress distribution over the guide bands. Now, once that solution is found, the engineer is able to read off a number of outputs from this calculator. First of all, and again in this particular example it's exaggerated, we can see what the bending or deflection is going to be across the entire length of the cylinder. That shape, of course, is superimposed over the guide bands, and so we get two stress distributions, a projected nonlinear stress distribution over the guide band and the 3D stress distribution that the guidance components carry. Now, in this particular example, the guidance system was not optimized, and so the engineer changes some of the parameters, including material and sizes, reruns the analysis, and evenly distributes the load over two guidance components. In doing so, after a number of iterations through this program, we achieve what's called an optimized guidance system. Once the system is optimized, we feel that the material will not yield, that the load is being evenly distributed. We can now settle in on the guidance package that would go into the cylinder. So why do we have to do this first? Take a look back at the previous slides. One of the key outputs, in addition, okay, so in the upper left-hand corner, we see this box of 3 guide bands where the load is being distributed over those 3 guide bands in a curvilinear fashion. So that's an important output for us. It tells us to use 3 guide bands, and it tells us that the maximum stress at the 6 o'clock position is going to be roughly 90. That's okay for this material. It's selected, and it shows us how the stress distribution is going to taper off over the full length of those 3 guide bands chosen. It also tells us that if we had any additional guide bands internal, so working inwards into the cylinder, they won't actually do much to carry the load. But a critical output that we get out of this calculator is something that's called a deflection at clearance. So our engineer can specify a clearance position within this cylinder, and we can determine what is the deflection of the rod, the whole system, as it moves off the center line. This is important for 2 reasons, at least 2 reasons. First of all, it allows us to investigate whether or not the rod is going to crash into the rod gland or if the piston is going to crash into the cylinder body. Even if that is maintained as a safe condition, where our gaps are large enough or our guidance system is designed properly to prevent metal-on-metal crashing, we also are able to use this number to understand what the true extrusion gap is. So if you're not familiar with the context of a extrusion gap, it's effectively the gap between the rod and the rod gland that when the rod seal is under pressure, that material could actually squeeze or be forced into this small gap between the 2 metal components. And if the material is strong enough, or if the pressure is low enough, or if the gap is small enough, no material flows into that gap. But if that gap gets too large, in this case, if we add on this deflection number to the nominal extrusion gaps on the drawings, we may be able to determine if the seal is made out of the appropriate material or if the seal design has to be modified in order to withstand the extrusion potential of the system. So that's why we have to do this side load analysis first in order to get our heads around not only the bearing components of the system, but to understand how the E-gaps are going to be affected, the extrusion gaps, as we move into the next step of this analysis, which is our extrusion calculation. So now that we know the deflection of the system, we can perform the extrusion analysis, which is the second step in this optimization process. So it cannot be performed without knowing what the total extrusion gap of the system actually is under load. And once we have that information, we can evaluate the extrusion potential. And in order to do that, System Seals has developed another calculation tool based on mathematical models from field observations. So for example, in the upper left-hand corner, we see a profile of a rod seal that has experienced either a gap that was too large, a pressure that was too high, a temperature that was too high, or a material that perhaps wasn't strong enough to withstand the extrusion potential in the system, and so that material extruded into the E-gap. And you can imagine over time, as this little tail continues to grow, material may break off. This process continues indefinitely until eventually there's a catastrophic failure. So we have these field observations. We've also run over 300 FEA simulations on various materials, conditions, temperature, and pressure scenarios, and conducted a number of laboratory experiments to confirm what our field observations and our FEA simulations are telling us. Once we have generated all of this data from the field observations, the FEA analysis, and the experiments, we can compile a calculator that allows us to predict the extrusion potential to interpolate between all of the variables that we've investigated in the past in order to determine whether or not a particular seal package will or will not extrude under the given circumstances. So if we take a look at a graph of the output of this particular calculator that we use, the black line is representing the extrusion potential or the stress, the von Mises stress, within the material that's chosen as a seal. Along the x-axis, we have the radial E-gap, so this would be the extrusion gap. And along the y-axis, we have the stress. The red line and the yellow-orange line represent limits at different temperature conditions. So for example, at 25 degrees Celsius, this particular material, at 60 degrees C and 69 megapascals of pressure, can see an extrusion gap of up to 3/4 of a millimeter before extrusion is a risk. I'm sorry, now that's at 25 degrees Celsius. If that material or the application heats up to 60 degrees Celsius, that limit is derated according to the material properties. So we know that material properties change as a function of temperature. We use a DMA in our laboratory, a dynamic mechanical analyzer, in order to determine how to derate these materials as a function of temperature. And in this case, at 60 degrees Celsius, this calculator tells us that extrusion will actually onset closer to 0.6 millimeters. And so in this case, we have a couple of options. We either have to redesign the sealing package, select a different material, or perhaps install an anti-extrusion backup ring. But again, we couldn't really perform this step until we understood what the true extrusion gap was that we obtained out of that bearing calculation that we did initially. And this calculator allows us to account for the material that's being used as a seal or backup ring, the pressure that's applied to the system, any engineering safety factors that are chosen, the extrusion gap, and of course the temperature of the application itself. Now once this step is complete, we're able to move on to a friction analysis because we've selected the seals, we know what materials the seals are going to be made out of, we know what pressures the system is going to be under. We can use research and testing that we've performed in our lab to predict what the friction will be in the system. So if we look at the graph in the upper right-hand corner of this slide, contrary to what we learn in most textbooks on basic friction, the coefficient of friction is actually not a constant. We know that as plastics and elastomers deform and start to conform around the sealing surface, coefficient of friction changes. In fact, it actually reduces. And so we've developed another calculator based on a series of experiments that we've conducted in our lab that for a given seal package, a given material, a given set of operating conditions, will predict the amount of friction that that seal package will generate as a function of applied pressure. And when we run this analysis, we take into account the fact that the coefficient of friction is actually a function that decreases with contact pressure. Now, after the seals have been selected, the friction analysis has been performed, the question remains, will the seals that have been selected function within the chemical or the fluid that they're supposed to be sealing? And so in order to answer this question, we've developed a fluid compatibility test program. It's a little bit different than the programs that you'll see in standard, maybe a hydraulic fluid cell sheet or a material cell sheet. So for example, a lot of the standards that exist today range from 7 days up to maybe 28 days or 1,000 hours at a maximum. But what we found in our testing over a number of years is that with durations of this time, there's a high rate of false positives, somewhere between maybe 15 and 25%. So that means 15 to 25% of the material options that are concluded to be compatible, in fact, would be shown to not be compatible if we were to do a longer investigation. So if we look at just one quick example of that, over 7 days, the change in this one particular tensile property increased by about 10%, and then it reduced back down to 0%. There was effectively no change. 7-day test, we would say this is compatible. But if we look at the results over 90 days, we see that even at the 1 month mark, 28 days, the property is only changed by negative 20%. What this means is that according to a 28-day test, this material fluid combination would still be deemed compatible, but if we look at the curve over 90 days, we see that there's a continual downward trend, and this particular property drops off to almost 50% of its original value. And by most standards, and by our internal standards, this is not a material combination, a material fluid combination that we would consider compatible. It is certainly not optimum. And so we've developed a 90-day test program at a minimum. In some specialized cases, we can even carry that testing out for 6 months or a year. But standard, we do 90 days. And we're looking at monitoring various parameters that relate to the tensile properties, elongation, tensile strength, various modulus values, yields, if we're dealing with thermoplastics, mass, density, and volumetric swell or contraction, changes in hardness, changes in compression set, changes in abrasion values, and important for low temperature applications, changes in the minimum service temperature limits. And we investigate this using something called a differential scanning calorimeter, which allows us to monitor the low temperature service limit for a material as it shifts over time as a result of being exposed to a fluid. Because even if a material is compatible with a given hydraulic fluid, that glass transition temperature has a tendency to shift higher. And so if you have an application that needs a negative 40 degrees Celsius TG and the material shifts from below that to above that as a result of the chemical that it's being exposed to, even if it's compatible from all of the other mechanical characteristics, we want to know this so that we don't run into a case where the seal becomes inelastic as a result of temperature shifting. So at this point, we've done a bearing calculation. We've optimized the guidance components. We have optimized the sealing components based on an extrusion analysis. We've performed a friction analysis. And now we've determined chemical compatibility as a part of this process. The final step in this process is to recommend surface finish parameters. So traditionally on engineering drawings for sealing components, we'll often encounter one specified variable, which is the RA, which is effectively a statistical average of the surface profile. But what we found in various surface finish experiments in our lab is that a number of other parameters matter. They're statistically significant. So for example, the RZ, the RT, and the bearing ratio have also shown themselves to be significant and important predictors for seal wear and for sealability in the long term. So with our laboratory equipment, we can actually specify and measure up to 9 independent surface finish parameters. But again, we typically think that these 4 are the ones that matter the most. And beyond the standard research that we've performed on chromed rods, stainless steel rods, we've also done some investigation on advanced material coatings. For example, in AGC or steel mill applications, a lot of times chrome is starting to be considered environmentally unfriendly, And so exotic coatings such as ceramic have been investigated, and we have surface finish recommendations, material combination recommendations that relate to exotic coatings such as ceramic as well, that have all come out of this surface finish research. And so this gets wrapped in to the COP process as a final recommendation. This usually ends up either in the COP booklet that is provided as an end result of this analysis, or it ends up on the proposal drawing with these parameters specified. So we just take a look at an example of some research that we've performed. In this particular case, we had 4 groups of surface parameter combinations that we were investigating. And again, we found that those 4 that we were investigating were statistically significant. That's why we see these nice tight bubbles. They're effectively lines that are telling us that there is a linear correlation between these parameters and the leak and wear characteristics that we were measuring. In this particular set of experiments, we see that group 1 was the worst performer. Groups 2 and 3 were increases in performance, and group 4 perhaps dropped off a bit, or within the measures of statistical error could be equal to the parameters that we investigated in group 3. And so it's research like this and optimization experiments like this that allow us to take our surface finish recommendations from basic standard recommendations and actually choose ones that optimize a parameter, perhaps minimizing wear or maximizing seal life. Okay, so as I mentioned previously, the end result of this COP process is a deliverable. This deliverable is a booklet that includes the analysis for the bearings, the extrusion analysis, the friction, chemical compatibility, surface finish recommendations, and the proposal drawing for the seal package that has now been optimized for that cylinder application. So what's the value for this kind of optimization program? Because we're talking about taking seal designs that work. We're not saying that a lot of these seal designs necessarily don't work. They do, but we're improving or optimizing a certain parameter, seal life, wear, and in this case, we feel that there is a reduced cost of ownership because we can reduce downtime, lower maintenance costs. We can lower the costs associated with replacing seals prematurely. If there are oil leaks being encountered because the seal package is actually not working, there may be savings in disposal and cleanup costs, especially for large-scale operations, and of course, an output in productivity and a long-term reduction in the cost of seals. Now, we can say this, but we feel that this is best highlighted if we show a few case studies, real-life examples where we've put this COP process into practice. And so let's take a look at our first case study. This was for a mill cylinder optimization project. This was a steel mill. There was a bending block, it's a block that bends steel, and there's these large hydraulic cylinders that apply force to bend. And the AGC OEM manufacturer was required to reduce the physical size of the cylinder in order to fit this cylinder into the physical constraints of the plant. So we use this optimization process to first investigate the existing design. So we put the existing design into our calculator, 4 guide bands in this particular case. Calculator ran through, determined what the loads would be based on the operating conditions, and determined that only 2 guide bands actually needed to be installed in this gland in order to safely carry the load. So why were we using 4? 4 was the design that was originally supplied. Something isn't broke, don't fix it. But in this case, we wanted to optimize it, and so we were able to safely remove the interior 2 guide bands, still safely carry the load, and distribute that load evenly over those guide bands. And as a result, reduce the gland height by 30%, which allowed the OEM to meet their target to get the cylinder to actually fit into the geometric constraints that they needed to. And of course, because we're shrinking the size of the cylinder, there is some material cost savings, some shipping cost savings, some softer savings along those lines as well. All right, so let's take a look at another example. Here's an example where we use this bearing calculator retroactively. So we use it as a diagnostic tool. This was not our cylinder in the first case, but this cylinder was experiencing a crash. The rod was crashing into the rod gland, and if you notice, this pattern of contact, this semicircle, is actually the nonlinear contact pattern that our calculator predicts should exist on the guide band. But instead, this contact pattern was being transferred to the rod gland because there was no guidance component in this portion of the cylinder. The guidance components were stuffed deeper inside the cylinder. So we ran the COP analysis on the current design. The COP calculator accurately predicted that the rod would in fact crash under those operating conditions, so it confirmed what was being seen already in the field. And then we were able to use the COP calculator, this bearing calculator, for the engineer to reposition some of the guidance components, change some of the materials, change some of the sizes of these guidance components, and in doing so, rebalance the load and prevent rod crashing from occurring. And so now the cylinder was fully supported, ultimately reducing the need to rebuild the cylinder prematurely due to this type of failure. Of course, we feel that if this analysis were performed at the beginning of the design process, this problem would have never been encountered in the first place. And our third case study, and our final case study, is something that cylinder rebuild shops encounter often. They rebuild cylinders. A lot of these cylinders have bronze components either in the rod gland or in the piston location. The piston is covered in bronze. It's called a bronze overlay. And every time the cylinder is rebuilt, the bronze overlay has to be machined down, rebronzed, so that the cylinder can go back into service. So we ran the analysis and found that although we still needed to keep bronze in the rod gland, the piston did not need bronze in order to carry the load. In fact, we could get away with using composite bearings, cutting grooves into the existing bronze, and simply replacing composite bearings as they wore out. And so what this optimization project did was effectively reduce the cost of maintenance and repair each time the cylinder was brought in. It wasn't failing, but the maintenance costs were high because of the bronze overlay. And now that step has been eliminated from the piston side of this cylinder because we were able to determine accurately, using these calculation tools, that polyester composite guidance components would carry the load on the piston side of the cylinder without causing a failure. So that's the overall summary of the cylinder optimization process. We do want to thank everyone for their participation and viewing up to this point. I think at this point we are going to open up the presentation for questions, and as I understand it, Mary will be moderating that, so I believe we can turn that over to her.
Yes, thank you so much, Kurt. Thank you for all the great information. We do have a couple questions in here, one that kind of came in early, one about whether or not the COP process can predict seal chatter in pneumatic cylinders. Is that a possibility?
Yeah, so the COP process by itself doesn't look at the performance of the seal in its dynamic functioning state. What we're looking at is the investigation of the guidance components and then the sealing components once the relationship has been determined. And so if we were looking at a side load condition or a condition where we suspect that overloading of the pneumatic cylinder were the case, we may run that cylinder through the side load process to see if, first, is there a bearing issue, and if there isn't, perhaps could this be a friction issue? We've seen in many cases where cylinders will chatter. It's a function of something called stiction or stick slip, where the coefficient of friction, the static coefficient of friction is actually lower than the dynamic coefficient of friction. And we would compare the observation that was taking place in the field with some of our friction research to see if that were occurring. Now, if it wasn't and our COP process couldn't predict it because the data wasn't available, of course, we have a research lab in our building at our disposal where we can run friction experiments for that particular cylinder with that material and under those operating conditions to see if that can be replicated, and then, of course, to see if it can be remedied.
Great. Another question from the same attendee actually is, if a small portion of a wear band is supporting the rod or piston, does this mean you can reduce wear band width?
Yeah, so now in terms of dimension, what we call width may be different than what the question is. So what we call the part height would be like from the front of the guide band to the rear of the guide band, and that's exactly what we use the COP process for. If we look at the one case study, if you imagine those 4 individual guide bands were just one long guide band, it would have said that we could reduce the height of that guide band effectively in half because we were able to pull 2 guide bands out. And so it's not that the load is carried just on the tippy top or the front portion of the guide band, but because from that front portion back, only a certain amount of guidance components are used, there will be a point at which adding more guidance is irrelevant because the rod is no longer contacting the guide band components. Now, one caveat to that is if you change the cross-section or the wall thickness of the guide band, you have to rerun the analysis because the pattern of contact spreads out. So in general, as the guide band gets thicker, you need a longer guide band in order to get the same stress distribution to carry the load. But for us, the question is always exactly by how much. And so that's what we use this calculator for, is to determine what is the optimum cross-section and also the optimum height, or what I think this question is referring to, the thickness of these guide bands. So yes, that's one of the things we use the process for specifically.
Great. We have one here in relation to temperature. How does the COP work if my application lives in a hot environment, for example, 150 degrees Fahrenheit?
Yeah, so that's a good question. In our bearing calculator, we do have an option to put in what the operating conditions are, including pressure and temperature. And once that temperature is taken into account, the material, the guidance material that's selected is derated. So the yield and the elastic modulus of the material both change as a function of temperature, and the bearing calculator accounts for both of those once the temperature is put into the calculator as an input. Now, once we move on to the extrusion analysis, we again have to account for the extrusion resistance potential of the material as a function of temperature, because the yield and the modulus both shift down as the temperature shifts up. And we account for the temperature behavior in that model as well. And then thirdly, we would account for temperature in the chemical compatibility, usually in that we are aging our studies at a temperature higher than the application in order to accelerate the behavior. So if we had a temperature of 150 degrees for the application, we may want to run our chemical compatibility test at 80 or 100 degrees Celsius in order to ensure that our results are accelerated so that we're not making predictions that are short-term for the material application.
Great. Here's something about mounting. It's clear how the rod ends generate torque, but what if my cylinder has a different mounting design, such as a trunnion mount?
Yes, that's a good question, because the video we show, the example was a spherical bearing on the cylinder end and a spherical bearing on the rod end. But we know that in the real world, we can have spherical bearings on one end or the other. The body can be fixed, like in a steel mill application or a fixed body hydraulic application, or we can have a trunnion mount. So our calculator actually has the option to select various different application end conditions, or we call boundary conditions, for the rod end as well as the cylinder body end, so that we make sure that we're calculating the bending and deflection according to how that cylinder is actually fixed.
Great. We just got another question come in here. Can the COP process help specify the best all-around seal and wear band to cover a wide range of conditions, such as would be used for a product line rather than a specific application?
Yeah, so that's sort of the opposite, right? So that's kind of the opposite of how the COP process works, because obviously we're trying to optimize for one particular application to get the best seal or sealing component package. But if we're talking about covering a product line, then what we would want to do is use the COP process to investigate the boundary conditions or the end conditions of the entire product line. So we would want to look at it at its low temperature, its high temperature, its low load, high load, small diameter, large diameter. And after a series of iterations under all of these conditions, we may find that there's one particular seal package that survives all of those conditions. And then, of course, maybe there could be some fine-tuning for different sizes, but if the end user says, no, we need one size and one package to fit all of these cases, we can use the COP tools to do that, but it's not optimized now. We've now generalized in order to fit a group of applications as opposed to optimizing for one specific application. But we can use the tools for that. That would sort of be an unorthodox way to do it, but of course the tools can be used to answer that question as well.
Great. I think we have one more question, so if anyone has any other questions, please make sure you submit them into the box. The final question is, I see a lot of published information about compressive strength with various composites and guide elements. Why is compressive strength not used in this analysis tool?
Yeah, so as we talked about material properties, the two I mentioned the most were the modulus, the linear modulus, or the Young's modulus, and then something else called the yield strength. And so when engineers design products to carry loads or to see repeated stresses, it's important to stay below the yield of the material. And the yield strength of a material is typically significantly lower than the compressive strength of a material. So in real designs, you're never designing based on the application applying loads anywhere near the compressive strength. We're always designing to be well below the yield strength in order to account for things like cycle loading, long-term fatigue, et cetera. And so it's not that we're ignoring it, it's that we don't need to use it because we're using a value, the yield strength, which is a much more conservative predictor of long-term performance of a material with respect to failure modes.
Great. That looks like all the questions we have for today. So if anyone thinks of anything after we disconnect, you can refer to the speaker bio box containing contact information for both Kurt and myself, and we will get back to you. Thank you once again, everyone, for attending this webinar from Fluid Power World, and thank you again, Kurt and System Seals, for this great information. As we said earlier, this presentation, thank you. As we said earlier, this presentation will be emailed to everyone later today and will also be available at fluidpowerworld.com. Thanks for being here. Bye-bye.